Hello. I said in my last talk that we were on the verge of a new kind of medicine. In this talk, I want to devote myself entirely to one single experiment to show that such an idea is not without currency, that it has actually, this experiment that is, been peer review published in this journal, which is a journal issued by the International Commission on Non-Ionizing Radiation Protection under the auspices of the proceedings of an international seminar on the effects of electromagnetic fields on the living environment at Ismaning in Germany in October 1999, and it's sponsored by ICNIRP and the World Health Organization and the Bundesamt für Strahlenschutz, German institute. Well, the experiment I want to look at is really rather amazing, and it shows that the electric fields of our bodies, not the magnetic fields now, it's the electric fields of our bodies, have a protective effect on our cells, and particularly on, in this case, our immune system cells, the white blood cells which protect us from infection. In a nutshell, as an abstract if you like, what the experiment did was to take some white blood cells out of a person and connect them to the person's body by means of an electric wire, but outside of the body, and being supported by nutrients so that they stayed alive. The cells were then examined by means of a test for viability called the trypan blue exclusion test, to show that the cells which had been exposed to the body's electric fields were far more, in fact significantly more, viable than cells which had not been so exposed. And so it was a way of showing that these electric fields we've been looking at as a means of diagnosis and treatment in medicine do actually exist, do have an influence, and are shown to do so in an experiment which anybody can replicate with the same equipment quite easily. It's a very easy experiment to do. So that's the experiment I want to talk about, and that's the abstract, if you like, of that experiment, which usually comes at the beginning of any write-up of an experiment as published in a peer-reviewed journal. And here's the actual experiment, if I can find it. It's the back of this book. Here we are. Here's the title of it, and you can see it says protective effect of a donor's cutaneous electric fields on lymphocyte viability, lymphocytes being white blood cells. And it was done in the first instance by myself and my then wife Tamara Galonia-Coghill at our laboratories in Pontypool. And I'll just read you the beginning of our study. It says, all living creatures emit weak but measurable electric fields from their skin surfaces as a result of endogenous processes such as heartbeat, cerebral rhythms, muscular movements, bone growth, digestive processes, etc. Exquisite sensitivity to such fields has been shown for some decades in sharks and rays, and my friend Ad Kalmin at the Scripps Institute showed that. In gymnacus fishes, which are fishes like those in the dark recesses of the Egyptian Nile, which can't see a thing in front of them, but they use electric fields to find their way. And that was first done in 1958 by Lissman and Machin at Cambridge. And many other organisms. And a scientist by the name of Warnke from the Saarland University has made a special study of all that. It says, although endogenous electric fields are known to regulate heartbeat rate and muscular movement, the function of cerebral rhythms have been the subject of speculation, with some theorists suggesting a morphogenetic role. And I'm thinking now of Lund, a scientist called Lund in the 1920s, who put forward that idea first. Experimental research, however, has reported inhibition of lymphocytes by electric fields, both at ELF and RF radio frequencies. And that's Dan Lyle, another friend of mine, who published a study in 1983, but has not identified any non-specific regulatory role or agreed mechanism. This study, this is our study, investigated the possibility that endogenous fields may play a hitherto unsuspected part in cellular immune system surveillance and regulatory growth control by means of a well-characterized test of viability known as trypan blue exclusion. And that's how we started writing up our experiment. And basically what we did was this. Tamara and I first isolated some lymphocytes from me. As it happens, I was the donor. And we took whole blood, and as a technique for getting the white blood cells out of the whole blood by means of centrifugation and drawing them off in a little band. Then we cultured them in a quite well-known cell culture which keeps them alive, called RPMI 64. That RPMI stands for Roswell Park Memorial Institute, and it's a well-known means of culturing cells. And we added a few other bits and pieces to make it even better, antimitotics for example. And then we divided those lymphocytes, that single spin of lymphocytes, into 3 little bottles. And here's a picture of the bottles, by the way they were put. Now one of them had a wire coming out. You can just perhaps see that. And that wire was connected to the skin of the donor, i.e. me. The next bottle, also with the same sample of lymphocytes in it, also had a gold wire coming out of it, but it didn't go anywhere. See that? And the third bottle didn't even have a gold wire. It was just put in there and left that way. And that box that you see holding them is made of mu metal. Now mu metal is, here's the box, this is what it looks like. Mu metal is a very soft iron, but it does have the benefit of keeping out any kind of radiation. So when we put the bottles inside this mu metal box, we knew that they wouldn't be affected by radiation coming into them from the atmosphere outside the box. Here's some of the gold wire. You can see it in that, inside that box there. I'll take some out so you can see it better. Here we are. This is it. This is gold wire. You can buy it in a jeweller's shop. You see that? There it is. And the bottles, here's an example of the way we seal the bottles. There is the bottle. If you could get it in focus, you can just see the wire coming out of it. If I bring it away a bit, you can see it better. See the wire coming out of the bottle, and that's the little bottle that we put it in. So we put these little bottles into the box like that. There's one inside, you see. And then we strapped this box, when we'd sealed it up, to the skin of me, the donor, so that the gold wire fed into one of the 3 tiny little files that I've shown you. Well, we then left that overnight. It's not too difficult. It didn't come off. It stayed where it was. And the next day, we then analysed each of the 3 sets of white blood cells, the lymphocytes. Now, in the way you do this is by using this dye. And what this dye does is, if the cell's skin, if you like, not the cytoplasm, but the membrane of the skin, is intact, then nothing happens. The white blood cell stays white. But with this particular dye, if there is any kind of crack or fall in the viability of the cell, and a hole in the membrane, if you like, it's degraded, then the dye turns the inside, the cytoplasm of the cell, bright blue, and you can really see the difference between the two. And so you can test for viability that way, and many laboratories use that test. This is a pretty standard, well-known test used throughout the world. And that's the test we used. And so we looked at the cells in the first bottle, and we counted the blue ones and we counted the white ones on a little grid, on a microscope slide with a grid etched into it, so that we could work out just how many of each kind there were, and then we could derive from that a percentage. So we had that. Then we went to the next bottle with a little gold wire sticking out of it but going nowhere. And we counted the white and the blue cells in that and worked out the percentage again. And then we did the same thing again for the third time, this time with the bottle with the cells in it which had been connected to the donor. And we counted the blue cells and the white cells. And what we found, and we repeated this 12 times to be sure, and what we found was that the viability, i.e. the number of white cells versus blue, in the bottle with the wire going onto the skin of the donor, i.e. me, was significantly higher by a long way than the other two. The other two were about the same in terms of percentage, but the one bottle with white blood cells in it coming from with the gold wire attached were significantly more viable. Now that's actually quite an interesting finding, because it can't be a magnetic field. A magnetic field doesn't travel down a wire the same way. A magnetic field will radiate equally from the source, and it will go back to its other pole. But an electric field being carried down a wire. So we knew it was an electric field effect because it was coming down a wire, and we could see that even though we did it 12 times, it took us a long time, we did it 12 times, we found that the viability was dramatically improved when there was the electric field of the donor present in the culture liquid. And here's some of the results. I've put them onto a page. There's 6 of them there. Look, it runs 1 to 6 down here, and this is the exposed. That's the one with the gold wire. The sham exposed, that's the one with the gold wire going nowhere, and the control, which is no gold wire. And what you see here are the percentages of viable cells. So if you look down the control one, I don't know whether you can see it, I'll try and... The control one has an average of around about 45%. And if you look down the sham exposed one, that's the one with the gold wire going nowhere, it's about the same. Hardly any different. But if you look down the one with the exposure to the skin and through the gold wire, you'll see that the percentage is in the 60s and 70s of percent viability. So it's significantly more viable. Now there was one interesting exception. In one of those sham exposed case, i.e. the gold wire going nowhere, you'll notice, if you look closely, that it's 80%. That's a very high percentage of viability. There you see, 80 point something. Even better in a way than the actual exposed ones, which was in the 70s more. Now we wondered why that was, and then when we looked again, what we found was that the little gold wire sticking out of the top of the bottle, but supposed to be going nowhere, had actually been touching the electric field wire coming from the skin. So it was, we didn't plan it that way, it just happened. But we did discover that that's why it had been so high. So we thought, well, there's the exception that proves the rule. And sure enough, it did. So that was the only time that it ever happened. All the other percentages were in the less than 50%. Well, we tried this same experiment a number of different ways. We tried using radio frequency fields. We tried instead of the donor's field, we tried using ELF fields instead of the donor's field. That's low frequency field. And in every case, we found that there was no effect of the electric field. In fact, what it did was the artificial electric field, it put the percentage even lower than the sham and the control percentages. So in fact, it was implying that there was an adverse effect on the white blood cells, if anything. So that's the experiment, and it's published, it's in the peer-reviewed literature. Anyone can repeat it. The method and materials are clearly set out. We tell you where to get the little boxes, we tell you where to get the gold wire, and we tell you where to get the bottles, which you can get from any pharmaceutical supplier. So that's it. And there we have it. That is an experiment which in the course of time, I think, may be regarded as somewhat important, because it is in a very replicable and hard science way showing that there is such a thing as an electric field, and it is specific to the donor. Nobody else's electric field had any effect whatsoever. So it was saying we do have these fields, they do have an important effect on the viability of our white blood cells, which in turn protect us from infection. But you know, it's all very well to do theoretical research or even bench research, but this particular experiment can have a very important practical application, because in deep surgery, when a lot of blood is lost, the blood has to be put back, and in many cases the patient's immune competence falls dramatically. It's lost a lot of white blood cells. These are its own white blood cells, they're not anybody else's. So what surgeons tend to do is to try to avoid loss of blood, and they keep the blood and try and put it back again. But if they were to use this technique of putting the white blood cells in an attached wire situation, just like we did in our experiment, then they would find that the viability of those white blood cells being returned to the patient to help them protect themselves from any graft host rejections or anything like that, the viability of those cells would be better than the viability of cells just put in a box somewhere out of the way until they could be returned. And that could be a very important addition to our medical knowledge. Well, that's just an example of the kind of experiments that we need to do in order to explore this new way of approaching medicine through electromagnetics rather than through chemistry. I'm not saying that chemistry doesn't work, and it's been a godsend to us all in the past, but I think it's time now that we started to explore these new methods, and that's one example of the kind of exploration that we should be having. Well, again, thanks for listening. It's a bit of a digression in a way, but it was an example I wanted to put before you of the kind of research necessary to understand better these invisible fields that surround us while we're alive. Well, thank you very much, and I'll talk to you again.